Today I will talk about inertial active particle in a Poiseuille flow. So this it is done by with my supervisor P.S. Burada. So when we observe the colloidal, when we observe the artificial microswimmers like this, and so vibrated rotors, we in these systems we observe that the particle are driven strongly or are larger. So unlike overdam systems, these particles, due to inertia, this particle has finite response time, and that affects the dynamics of the particle to a great extent. So the question that we are asking, so how does inertia affects active particle dynamics in a flow, particular in Poiseuille flow? So let me explain the system first. So we have an active particle in a two-dimensional channel with under Poiseuille flow. So as we see from this schematic, so the velocity direction, the flow direction is positive in along x direction, and so velocity of the flow changes along y direction, and this form the parabolic path. So, but because of this, the shear this create a shears, and which is weaker at the channel center of the channel and stronger at the channel walls. So this shear tries to rotate the particles and tries to rotate the particles. So here we have a self propulsion, flow, Poiseuille flow, and local shear induced rotation, and they are competing with each other. So we model this system using overdamped, underdamped Langevin equation. So where we have considered the inertia of the particle. So the translational motion of the particle is governed by the force balance. So this first term represent inertial force. The second, this correspond to viscous drag from the surrounding fluid. This is the active force that drive the particles along its orientation. N cap is the orientation vector. So it is the advection from the surrounding Poiseuille flow, which act along the channel direction, and this is the noise, translational noise, which is modeled using the Gaussian white noise. So on the top of that, the orientation of the particle evolved that governs in time, and that governs by the rotation induced local shear induced rotation. This is the intrinsic angular velocity, and this is the orientation noise. So what the key point here is that because of inertia, there is the velocity direction does not instantaneously follows its orientation. That create a lag. This is the inertial delay. For that we have plotted the orientation of the particle and velocity direction for different mass values. So in for lower mass value in overdamped regime, we clearly see that they are overlapping with each other. But as mass increases, we clearly see here there is a phase lag between the orientation and velocity. So and this inertial delay is experimentally verified using these vibrated rotors, and here we can clearly see that by the Loven groups, and here we clearly see that how particles orientation and velocity directions are in different directions. So and this inertial delay affects the particle trajectory in a Poiseuille flow type systems. So that that we can see from these figures. So in this panel, in these three panels, we have a particle trajectories for different mass values. So we for overdamped regime, we are observing the symmetric oscillatory motions, and the key point is that the particles are moving opposite to the flow direction, showing the upstream motions. So particle are starting from here, and it is moving towards the negative x direction. And similar, so these insets are the experimental results in overdamped case, and here we also see the similar oscillatory trajectories. So but as we increasing the mass, so we can clearly see that particles are moving towards the positive x direction. So there is a transition from downstream motion to upstream motion, and then when we further increase the mass of the particle, the particle localized near the wall, and inertial, because of inertia of the particle, we clearly see that there is a transition from downstream motion to upstream motion to downstream motion as we increasing the mass. So to characterize this behavior, then we look for the transport characteristic, and we plotted here the average velocity and d effective as a function of mass. So for different noise strength. So in panel A, in lower mass regime, we clearly see that we are getting the negative average velocity. That if that quantify that we observe the upstream motions from the particle trajectories. So as the mass increases, we clearly see that there is a transition from downstream motion to upstream motion, because the average velocity going from negative to positive, and it attains a peak at the intermediate regime, and then it decay because in this regime inertial force dominates. So at the intermediate mass regime, the transport is maximized because the force acting on the particle, the effect of flow and self propulsion balance out, and we get the maximum transport at this intermediate regime. So here we clearly see that at the same intermediate mass regime, we are getting the enhanced effective diffusion, peak in the effective diffusion, and then so in this way we clearly see that there are three crossover region here. So in the lower mass regime, particle are showing the upstream motion at the intermediate, and then at the intermediate regime we get the downstream motion, but with maximum transport, and then there is a trap along the walls. So these are the steady state transport of the particle, steady state distribution of particle along the channel for different noise strength. For lower noise strength, particle are accumulate near the walls, and they moves, but at higher noise strength particle, the distribution of particle are uniform across the channel. So here we observe the effect of activity. So as we increase the active force, that support the upstream motion at the lower mass regime. So here we can clearly see that as we increasing the activity, we are getting the downstream motions. So but it limit by the inertia. So this is the conclusion. So we have upstream motions at the lower mass, and but these results are prominent in transport property, and we can separate particle depending upon the mass, because at the there is a particular mass value, we are getting the peak in the average velocity. So this can be used to sort the particles. So this is for more details you can follow this article. Thank you for it.
Any questions?
Is it possible to physically understand the transition? I mean, I really didn't understand why for M in very large, it should go to the wall.
Okay, so you are, why it is showing up?
Yeah, like the green curve, I didn't understand.
So, so there is a flow along the direction, across the channel direction. So the flow tries to move the particle along positive x direction. But why it is moving in the opposite direction? Because there is a constant, there is the orient activity, and there is a local shear. When particle moving towards the channel, it's try to rotate in the opposite direction. But at intermediate regime, the particle tends to move. Okay, particles try to move along the channel direction because it follows the flow strength. So up to some time, time it follows the flow direction, because there is a flow strength is also which tries to move particle in a positive direction. So because particle are moving, look, maximum time spent by the particle is near the ball here because because of this shear force acting on the particle. So that particles want to move in this oscillatory motion. So whenever it moves coming towards the end of the ball, it tries to rotate. So it spend more time near the balls.
Okay, let's thank the speaker again. Please.